So at the end of the session, Shomik will take over. Okay. Okay. Arman, please start.
Thank you, sir, introducing me. Can you hear me, sir? Hello, can you hear me?
Yeah. We can
we can.
carry on.
Okay. Okay, so I will be talking about the uh, comparison between the compass state and the different type of superposition with the help of squeezing and displacement operator. So basically, in this this is a recent work. I'm looking here how this compass state can be produced with the help of the application of the either squeezing or displacement in the phase space. So contents I will introduce what are the patch state and the compass state, and their by their what are their uses. Then Agarwal's work that showed how to produce cat state, which was given by in the 1994. Then I will introduce propose two state, which will help us to approximate these compass states. And by studying their property beginner function, number distribution, and fidelity. So this will allow us to compare our proposed state with the compass state. Then for sake of that as compass state has some properties of property that they are highly sensitive to the external fluctuation to the system. So that are characterized by the variance of the fluctuation they are being sensed by the system. So, that we also compare. Then we will look the Hamiltonian for these proposals. Then I will summarize.
Little more loudly.
So-
Little more loudly.
Okay.
Yeah.
Okay.
Yeah, now it's okay.
Okay, so what are the cat state? Before that, I will also tell what are the coherent state. Coherent states are the superposition in the infinite dimensional Hilbert space, such as Cox space, and which those states have a Poissonian statics, and they follow the minimum uncertainty principle in the phase space. So these cat states are the superposition of two type of the coherent state. In this case, we take the alpha and with the negative sign alpha, which describe the two opposite location in the phase space position momentum, and theta describe the relative phase between the two these two coherent state. So compass state again is the for superposition of four type of the coherent north, south, and the east and west. These four type of coherent state with the same type of magnitude, which is described by mode of this alpha. So these cat state actually they can be found in the double well potential. So ground state describe the even cat state of the double well potential, while odd state will be excited state of this double well potential. This cat and cat states. So there is exist current type of interaction. So in the evolution, time of evolution of the coherent state in the presence of current type interaction, this type of the cat state and compass state, they can be seen. While this current type of the interaction also produces three type of the coherent state superposition, but as well as the six type of the superposition of the coherent states. But current medium has a property of dephasing. This cat state and the compass state also dephase very fast in that current type of the interaction. So this cat state, these are the eigenstate of the two exponents of the annihilation operator, while compass state is the eigenstate of the four exponent of the annihilation operator. So this cat state and compass state has a property of coming back to the original parity state after losing for the gas state 2 photon loss and after losing 4 photon loss after yes, uh, so this type of the also beneficial in the quantum error correction because if any information defined in the but either in the gas state or compass state because of the reverting to the initial state after loss in the cavity the our information can be obtained. So another property of using this these states is that if we encode the logical information in the higher dimension space, this also allows us to preserve the information for the longer time. With the increase of the coherent amplitude, so there is also increase of the correction probability of the error in the system. And the one most important property of this gas state and compass state, they have a oscillatory phase space structures in the due to those oscillatory structure in the phase space, these become highly sensitive to the small perturbations. So now I will talk about the Agarwal's work, how these states can be experimentally produced. So Agarwal work basically was related to the use of the squeeze state and subtracting single photon. So he studied the properties such as again Wigner function in the presence of the damping and also absence of the damping. So but he found that after losing single photon from the squeeze state, which is also equivalent saying in the squeezing single photon, he found that it has a Wigner function similar to the cat state, as well as the other properties such as the statics of the cat state, which was approximately was same with the cat state. So how the experimentally they are produced? So use same effect, that the damping effect is produced by the beam split. So you take the squeezed vacuum state as an input to the beam split and allow to transmit 3 to 4% of the light to one port, while in the other output port you will obtain approximately a cat state. But this method is only available for the small amplitude production. So this remain challenge for the four type of the state, cat state and compass state, to be produced in the large amplitude cases. Okay. So here we see now Wigner function for the how we did that. So this is single photon Wigner function on the left hand side with the dip in the center, which describes the negative value. So single photon is also excited state and odd with the odd parity. So negative value is here at the origin also showing that it has the odd parity. So on the right hand side, if you apply now squeezing, so this squeezes in the in the momentum direction. So this describes squeeze photon subtracted squeezed state Wigner function on the right hand side. Now if you allow it to damp in the system, so this kind of thing on the left hand side, this Wigner function becomes with the loss. It has a nice smooth interference pattern in between and with two Gaussian lobes, top and bottom. So this was his work. So on the right hand side is this again the same state but with the displacement of it. So for the position of the two state, we use this displacement squeeze state, single photon squeeze state with the two type of the displacement. So now you say if we have the cat state with d alpha plus d minus alpha, so this if we now squeeze these two of the axons, application of the single photon state, which will again look like this on the plot on the right hand side. We will have this same cat state on the left hand side, and another cat state will be on the left hand side with some interface pattern in between. So this is the analogy for the first type of the proposition for the comparison between the compass state. So another possibility is that we can have a compass state that we can use two type of the orientation of the squeezing. So we can squeeze number state with either in the x direction, either in the p direction. So here positive R and minus are described the either squeezing happening in the x direction or in the p direction in the phase space for the oscillator state. And so if we compare now, if we do qualitative analysis, so for that we calculate the beginning function, which is calculated with the help of this formula. Expectation of the displaced parity operator. So pi is the e raised to power I pi a diagram. So it's parity operator for the infinite dimension Hilbert space. So this beginner function has a property that when it is greater than 0, it shows it describes a measure as a for the classical state. But when it has a negative value, so it shows the antisymmetrical part or in the wave function, which is deviation from the classical nature. So now if we see the beginner function for now compass state, so this is it has a core Gaussian law, which describes as a yellow part in the figure, and with the central interference pattern that is highly oscillator with the small square spots. This small square spot actually makes this state and this compass state highly sensitive to the small fluctuation because of these small fringes. Due to presence of small fluctuation, these fringes has a shape in the phase space. So with the help of beginner tomograph, we can actually measure those type of fringe shapes in the experiments, which in turn allow us to measure small fluctuation external to the system. So this is the beginner function for the compass state. Now if we plot beginner function for the first state, that was our squeeze operator, then superposition of the two type, the displacement operator. So if we say in the left hand side for n equal to 1 for the first oscillator state, so on the left hand side we have a central interface pattern and two types of the cat state, which was same as we thought in the initial case. So this blue part shows the interference pattern, which signifies as cat state, while interference pattern from the center, which look like the compass state. For the n equal to 2, it has large number of interference spores, which does not look like our compass state, but for a more analysis, we can do fidelity calculation to come out far it from the compass state. So we also plot for the second state. So here we take the for the n equal to 1, we see that the blue part is showing a negative, but it does not have a interference pattern comes out at if we do no matter how much squeezing we apply, either in the x direction or in the p direction for n equal to. But n equal to 2, for our second state, we have a squeezing in this direction and squeezing in this direction, which has also interference pattern with the 4 blue dot. So it has a 4 Gaussian law clearly coming out, which is similar to our compass state. So in this case, if we look for n equal to 3 or n equal to 4, you will see that more interference pattern will come out for our second state with the with for Gaussian laws. For another comparison, we did it number distribution. So for the number distribution, we chose our for initial compass state with the different phases. So mine here the magnitude -1 raised to power -7 define different relative phase for our compass state. So so comparison here is that for the psi1, our first state, and ks psi0 ks is our 0 describes L equal to 0, our assumed state, compass state. So in this case, we see that it has a nice non-zero component of with the compass state, with n zero component remains with the 0, matches with this. For the second state, it has a similar probability distribution. Now, if we do more quantitative analysis, so we see that for our second state from first four data points have very much close, but they will be very much close to the one value 0.99, 0.99, 0.9. So this is for our second state. But for this first case, what happens that for n equal to 1, it has close to the 1 value, but n equal to 2, it start producing value. We also saw for n equal to 2, equal to 4 for our first state, fidelity start decreasing. In this case, for the second state, we also have large value of the beta. So this shows the compass state for comparison of the compass state with our second state will have larger value of the beta, as well as fidelity will be also large. But in our first case, for the first state that we have proposed, only n equal to 1 will have a large fidelity. But for n equal to 2 or 3 more than the n equal to 1, will have smaller value fidelity and will not support larger value of the beta, which is described the amplitude of the compass state. So our second state is potential candidate for the production of the compass state. So another property we studied here is the sensitivity of a compass state, and that we compared it with our first state and second state. So how this sensitivity is calculated? So first we how in the experiment is actually these sensitivities are calculated. So first we take a probe state as a prepared in the cavity state. In the cavity, then we allow number of atom two levels atom pass through the cavity. If as these two level atom interact with the field inside the cavity, and then after it comes out of the cavity, we measure its excited state probability. So by the formula that P equal to psi d delta psi, that delta here describes that any fluctuation happen during this interaction with the cavity field. So this delta can be found by reversing this formula. Once we know experiment from this experiment PE, then we will have the delta value. So in the estimation of this delta value, we can there is a variance associated with this measurement of the small fluctuation. So this variance is also calculated by the formula of the conversion of binomial probability to the normal distribution. So if we have n types of the measurement of the two level atom after interaction with the cavity field, so and if we found excited state m times, then by binomial conversion to the normal distribution, we will have the variance equal to the n PEPG. This variance will describe how much error is associated in the measurement of this small fluctuation, which describe the. So now this variance is actually criteria for the sensitivity. So now for the compass state, either L equal to 1 on the left hand side or an L equal to 0 on the right hand side. So we see that red line is so the average photon, this average number photon to describe the resource for the cavity for the measurement of the small fluctuation outside the system. So if this as here we see that as average number of photons going up, so this variance is also going down for the compass. On the right hand side, we also see the same behavior as average number of photons going up, and this variance is also going down. This is true for the compass state. Now, if we now take our first state, now we see that n equal to 0, our first state actually becomes a cat state. So cat state has a property of measurement of small fluctuation only along to the along one direction, while compass state has a sensitivity in the two direction in the phase space. So n equal to 0 here describes the cat state. We see here that as the red lines that resources go up, our green line describe theta equal to pi by 2. Theta equal to pi by 2 is the now direction of sensitivity. So in this direction, variance is going down. In this sensitivity direction is actually in that direction where interference pattern is has a axis. While blue line here shows the theta equal to 0. In this direction, there is no interference pattern. So in this direction, this remains constant. It does not actually get affected with the resources. So only the green lines. While n equal to 1, we see that every lines gets affected, which is we also saw in the fertility table that n equal to 1 it has a large fertility with the compass state. So compass state is in the both directions, theta equal to pi by 2 and theta equal to 0 has a sensitivity and this is going down, similar to the compass state as resources go up. So for the second state, which is we said that which has very large, very close to the fertility is very close to the 1. So for every cases as the resources go up, variance that is blue solid lines goes down. For this on the right hand side, again dotted lines describes the resources that are going up, while our variance is going down, which are described the solid lines. Delta square is they are going. So up to this now, these are that variance or Wigner function of fidelity. They are in the grade. They show that our second state is a could be a great candidate in the preparation of the compass state. While the first case with the n equal to 1, which has also a large probability, large overlap to find the compass state in the Hamiltonian, which will have this type of the eigenstate. So now I will describe the what type of the interaction exist, which will describe these our two type of the state. So our proposed state, first proposed state can be prepared, and the rapid type of the interaction here rapid type interaction will allow us to produce two type of the displacement operator superposition while two photon this capital G interaction which describe two photon drive it will allow us to produce squeezing in the state in a single photon rapid type interaction, and with the help of two photon drive we will be able to produce our first type state, which is squeezed display superposition of displacement operators. And in the cavity QD, this small g has not been yet obtained large. So with the help of circuit QD, so G can exist large this the field and atomic interaction. So in the circuit QD, we can actually, if we want, have to have large alpha value of the compass state. So this G will help in the circuit QD. In the two photon rapid interaction, it will help us to produce our second type of state. This type of interaction actually also find in the circuit QD. This this type of interaction actually be obtained by applying the bias current to the resonator line in the presence of squared, which will allow us to cancel out the linear term, which is like single photon, like in our first type of Hamiltonian. It will allow us to cancel the linear interaction while only letting us to have our leading term with the two type of photon interaction with a qubit. So the summary of this one, we compared the number distribution, Wigner function, and overlap, which is which actually shows that this overlap is very close to the one for the our second state, proposed state, and first type of proposed state for the n equal to 1. So for the reference, this was the first reference is the work of the Agarwal, which shows that photons are subject to squeeze state source preparation of the gas state. While the other reference is a recent paper in 2020 that showed again compass state preparation using gas state by similar of the Agarwal. Okay, thank you. If anybody have question can ask.
If anybody have any question, please ask. There is no question in the chat as well.
Yeah, I have one small question. Arman, what the status of this measurements in the continuous variable states, like for example, parity or in the context of parity codes and things like that?
Yes, sir. And there is also a recent paper was again this in this group. So this was PRL paper. So they actually use the preparation describe the preparation of GKP state. They also are actually another version of the compass state, which they allow the squeeze, the use of the high squeeze squeezing. So actually this interference pattern becomes more smaller than the that present in the compass state or the gas state. So they are actually they are also given the only proposal, but it was not an experimental paper. So people are actually trying to prepare this again this type of states. They like.
Okay. See, one could also think about circuit QED, no? Circuit
Circuit,
switch.
yes, yes, yes. I think in the optical platform, this type of state only be useful in context of metrology. But people want to use in terms of the doing quantum computation or error correction, then circuit QD is like first choice. Because they need the setup very small. So circuit QD will be on the chip.
Thank you.
Yeah, we also sincerely thank Arman Bhaiya for taking up the slot as in such a short notice, as our original speaker, Professor Usha Devi, was unavailable today.
Yeah.
So we'll end this session now, and our next session starts from 3 p.m. IST. We have two exciting talks, one from Professor Marcus and Muller and one from Professor Bob Koike. So thanks again to all the participants for your kind attendance, and we hope that you will be present in the next session as well, which starts from 3 p.m. today. Thank you all.